Get this going. All right.
It's made up. That is falsified.
In my device too.
In the device too. Dude, it's about to be.
What's happening?
The thing is that he can't, like, oh god.
Cole's making fun.
Good.
Cole never said anything. I don't know.
I'm waiting on my bread to finish toast.
Yeah, and only that, right?
Yep.
Man's also called me old. I can't believe to finish it.
How old are you?
I was 16, but I was thinking, like, September by Earth, Warm Fire.
What? What did you say? September, Earth, Wind, and Fire?
Yeah.
What that is.
Yeah, well, I was just humming that, and he was like, how old are you? That's when my mom was young. I looked at him, I was like, I am 179 years old.
916 stuff, dude. Stuff. It's a hard life to live.
So it's a hard life being able to fit in.
Nice.
Is it just over the goose dog goose down thing?
It's only those 10 words.
Really?
Yeah.
Easy.
How to
Conjugate them?
Yeah.
Easy.
Was it?
Just the thing that we're supposed to study for Spanish. It was the thing that we did last week. Oh, it's just it's really easy.
Awesome.
I don't care.
What kind of do you have a single piece of toast?
Yeah. Okay.
Just one?
Listen, we have more bread. The problem is it's out the fridge right now because we're out of.
So you took a single piece of
There was
toast.
one piece left inside the bag.
Well, I know,
That's
but
bad.
Is that your whole lunch?
Yeah.
Is that just regular bread?
It's just white bread.
Is there anything on it?
Butter.
That's it? Like nothing.
Butter is amazing.
But you could have like had garlic bread or something. Like you put a little garlic bread.
Garlic butter. Oh my gosh. You know, it's actually really good. Untoasted white bread, and you put some butter on it, and you sprinkle some sugar on it.
Sugar toast, obviously. What do you mean?
It's sugar, white bread, and butter. How can it not be good?
It's just
Ethan, you know what's even better? Your prime.
Yeah. Which we have the same one of. He didn't know.
No.
how long is this shit gonna go on?
There, sorry.
It's not even fun.
It is though. We have the same thing.
And
Yeah, that was the first thing he told me when he came over to my house one time. He was like, "Wow, bro, he has the same permit." And I was like, "Cool."
You know, friendship is real. What?
When you told me he has the same permit.
All right. Break them.
one would have.
Yeah, that might work better.
You actually get a chair in there.
There's a chair.
And she finds out you have a.
There we go.
Your chair is against the wall.
I don't
There's one in the middle.
I don't know
I'm
why.
having way more trouble than I should. There we go. Thank you.
I was bored.
Wow.
I just have my shoe, bro.
But why are your shoes on?
Why are you, you're not my bro, homie.
Alrighty, I'm coming. Sorry for the delay. I have to deal with it.
Take your turn.
Ethan, remind me to never make your sister angry. And we're good. Take this off, so I'm still in my apron and I'm hot. Hey, Pepper. Okay. Yeah, that was mine. Right. Okay, I'm back. So you guys had lots of work this week. And that's because I was trying to help you guys really sort of nail home this new stuff. Let me make sure I don't have anybody else in the waiting room or anything. Okay, I don't. Okay, so my confession time is that naming has always been hard for me. And so for me, I have to look at something because I have a hard time remembering all those rules. Now, how many of you noticed that there's a massive cheat sheet in your preface in your binder?
What?
I love it. I love it. Go to page 19 in your binder and tell me what's there. And no, I didn't tell you last week because I was hoping you guys would. Page 19 in the preface. Tell me what you got. Oh, look, a flow chart. Oh, look, a flow chart. Oh, this is why we look over our binders before class.
Yeah, I've seen it before. All
Yeah,
that time Googling.
all that time Googling it. Okay, so I'll tell you right now, I have, when it comes to being asked to name a compound or anything of that sort, I have no problem with you guys using that plus this to get your answer. That tells me you understand the process behind it. If during that you happen to memorize the stuff, out freaking standing. But if you don't, it is not the end of the world, because unless you're going into a science that is going to involve lots of chemistry, you won't need them memorized. It's not practical in your life, right? If it's going to be practical for you, like if you think you're going into biomed or biology or chemistry, and does anybody want to go into, Michael, Cole, y'all with me? Anybody planning to go into medicine or science or anything like that? Yeah, then you may want to memorize your flow chart. But if you're not, right, it's pretty practical. It's pretty helpful. So I'm the kind of person that has to stop and listen and look at it that way. Here comes Alex. Good, she didn't miss any of the weirdness of the. Yeah, because that was fun. All right, so since everybody is here, I think that's coming. I am going to, I have a slideshow, and it'll be over there, but it's mostly for whoever's online. And then I will also save the slides as they are for you guys to go back and review. But I'm curious to see how much you guys got done on your own, because it certainly wasn't easy. So you did them all by yourself, right? Yeah, you guys are never on the phone in the wee hours of the night doing.
We started at
Science.
9 and we were still up at 11 doing it.
Yeah, it was a lot. So not the end of it.
We
Real
started
fun.
at a
Yeah.
game for lack of a better word.
Not the end of the world if you didn't get it all done, but certainly worth trying, right? All right, so this week we're talking about simple ions, ionic bonds and salts, and the naming. Now there are some apps you can get. Did anybody see the email last week? I listed a bunch of apps. Oh, shush. So I listed a bunch of apps last week, and I have a whole file of chemistry apps on my phone. And there is I have this whole file of them. There is an app that's a nomenclature app, but it doesn't start with stuff this simple. It's kind of leads more towards the organic chemistry, because like its categories are alleles, cycloalkanes, alcohols, aromatics, ketones. So it's a little higher level, but if you go online, you can put in like ionic compound naming flashcards, and they're there. And that can help you just kind of practice, sort of just to compete against yourself, you know, if you like that sort of thing. Some of us do. I picked particularly obnoxious backgrounds this week because, you know, I was thinking about electricity and electrons and flashy lights. So anyway. All right, so the first page in your notes. An atom or group of atoms that has a positive or negative charge because it gained or lost an electron. What's that? Those are ions. Okay, so that's easy. So looking up here at our periodic table, which I love having right here because it's so big. So if we look, I was reviewing this with the other group too. So remember that vertically, they're groups, right? And that means they all have the same number of what? Yes, this adding. And going across horizontally, they are periods, and that means they have the same number of what? Energy shells. Shells.
Yeah.
Okay. So what you're going to want to do is when you're looking at an element that's going to become an ion. Like look at fluorine or chlorine. Okay, so what group are they in?
Halogens.
That's right. And do you know what number that group would be?
Which one?
7.
17. Yep, 17. 7 is the answer for valence electrons, right?
Yeah.
So how many valence electrons do you want? Right there. What's your special number?
8.
8. Yeah, because you're going for your octet rule. You want 8, right?
Oh,
So compare fluorine to, say, lithium. Okay. Lithium has how many valence electrons?
1.
1. Okay. Is it going to be easier for a lithium to lose or gain?
Lose.
Lose. And is it going to be easier for a fluorine to lose or gain?
Gain.
Right. Okay. So that's what you got to keep in mind when you're talking about ionization energy. That's what you're talking about. How much energy does it take to basically turn yourself into an ion? Woo. Okay. So your sodium ion has how many protons? 11. And how many neutrons? 11. And how many electrons
10.
in the sodium ion? Yes, 10. Why are we saying 10 and not 11?
Because it lost 1.
Because it lost 1, because it's an ion, right? Not just the regular sodium atom. Because it's would have 11 and it's much easier to lose 1. Now we use sodium chloride today, right? And we use potassium chloride today. Look at where they're situated on the chart. Chlorine needs how many to get to 8?
1.
Needs to have 1. Sodium needs to lose how many to get to a full shell? 1. So see why they go together? All right, there you go. So in most chemical reactions, atoms tend to match the outer electron configuration of noble gases. And that's called the what?
Octet.
Atta girl. Octet rule. Okay, yes. So 8 is a happy number for your outer valence for most things.
Unless
Yeah,
hydrogen.
Unless you're 2, you're helium, right? Okay.
Or hydrogen.
Yeah. That's not a noble gas, really. So we'll look over here for these guys that have full outer shells. If they have a full outer shell, they're not going to be very reactive, right? They can't be reactive. It's when they need or want to get rid of electrons to get to that same kind of configuration that they are reactive. So what do we get for number 4? Who wants to do the complete sentence for me? Abby.
An anion is an ion with a negative charge.
There you go. And go ahead.
Valence electrons occupy the outermost energy level of an atom.
That's right. There you go. Excellent. And how about number 6? Who wants to do that one?
I wasn't able to find it.
Yeah, same.
So the chlorine ion,
6 and 9
it's
really should be
dumb. It's different. That's the word you're looking for. I know. Abby guessed right. I know. I looked at it too, and I was like, wait a minute. Because see, you're going to see less of this particular workbook enrichment stuff next semester, because I pulled it from one of my supplemental materials, and all of the teacher guide was online, and then they took it off about 3 weeks ago. They took away all the answers. So I have to go through and get all the answers, which is fine, but I want to make sure they're right. Make sure I didn't mess something up. So I had to go through a lot to kind of find them. So I finally found different and was like, really? So your anion is negative and your cation is what? Positive, right? Okay. And then this last one says that many stable electrons have a configuration of, yeah, that's what we were just talking about. You guys are perfect. All right, so here's my little deal that helps you remember. Some of you know this one from last year. Up there is our cation. And he's an ion with a positive charge. He's the cutest ion ever.
so cute, isn't he?
He's the cutest ion ever. If you can remember that, there you go. And then there's your anion. Oh, he's so angry. He's an anion with a negative attitude. An onion. Think of him like a little onion. He's grunchy. Hey, you coming here? No. He's grouchy. I don't know. I like silly things.
Oh, I don't think Michael gets it. Can you explain to him a little more? Yeah.
So, Michael, that kitty is positive. No. All right, so number 9 in your notes. How do the outer shell electron configurations of group 1, 2, 15, 16, 17 compare with those of the noble gases?
They're incomplete.
They are incomplete. That is right. Anybody have anything to add to it?
No.
No. So 1 and 2 have the same electron configuration as noble gas in the previous period. So if you think about that, 1 and 2, group 1 and 2 have the same electron configuration as the noble gas in the previous period, which is sort of, if you're looking at 1,
Because no,
And-
don't look at it.
and then it says group 15, 16, 17 ions have the same electron configuration as the noble gas following them in the period. So what that means is what we just said. If you're over on this side of the table, you want to lose electrons to look like the noble gas in the previous period. So if you're potassium, your goal is to look like what?
Argon?
Yes, right. And if you're sodium, you're trying to be
Neon.
neon configuration. Absolutely. And if you're, okay, so then if you're chlorine, what are you trying to be?
Chlorine, argon.
Yes, argon. And if you're bromine, you're trying to be
Krypton.
krypton. Exactly. We get it? So 1 and 2 have the same electron configuration as noble gas in the previous period. 15, 16, 17 have the same electron configuration as noble gas.
It's trying to be a pirate.
Period following them. Yeah, there you go. So what do you notice about all the ionic charges for group 1, 2, 15, 16, 17?
1 and 2 are positive, and then 15, 16, 17 negative.
There she goes. Okay, so 1 and 2 are positive because they're doing what? Getting rid of those electrons, which is going to make them more positive because the electrons are negative.
They become cat ions.
There you go. And then they're going to become cation ions. That's right. And then you've got 15, 16, 17. They're going to gain electrons. So they're going to become not just negative, but negative by 3, 2, or 1. Whereas the cations are going to be 1 or 2. Does that make sense? It's right there. You're looking for it. There you go. So how many valence electrons do atoms in group 1, 2, 15, 16, and 17 have?
Well, in group 1 is 1, group 2 is 2, 5, 6, 7.
There you go. It's right there in the number.
1, 2, 5.
1, 2, 5, 6, 7. Excellent.
No, so he's just lying on his-
That dog is so spoiled.
No, he's not. I'm
So-
giving him a belly rub, but what?
Here are your valence electrons here for group 1. And if you look at this picture, it'll show you. That's like an electron dot diagram. Do you guys remember those?
Yeah.
It's when you draw the symbol and then you put dots around it for the valence electron configuration. So obviously in group 1, it's just going to have the 1 dot, and in 2, it would have 2 dots, etc. Right? And group 18 have 8 valence electrons, except which one? Helium. Why?
It's number 2.
It's number 2.
Not
So
number
it's only got 2. And when you're doing these, you skip groups 3 through 12. Those are your transition elements because they vary. We're not even messing with them yet. We're not going there at the moment. Nope. We're going to stay on the outsides of the table right now where things are a little more simple. We are not going there. No, we're not. So what do we have going down the table? We've got, who knows them? Who can read them from here or knows them without having to read what they are?
What do you mean?
Are you saying
Lithium?
hydrogen?
I mean, what are the names?
Oh,
You know them
lithium,
yet.
sodium, potassium. I don't
Rubidium,
know.
Rubidium.
Rubidium.
cesium,
Francium. Yeah. Okay, good. That's what I'm wondering. Is how do you know?
Frankly, that last.
Yeah. Some of them are really like, look at number 106.
Lead TB. I don't understand that.
What's number 6?
I was on to be.
Carbon.
Seaborgium. Yeah, 106. And then look at
Cyborgs.
104.
Rutherford.
Rutherfordium. So obviously
That one's
that's
named after Rutherford.
Rutherford. There you go. And then you have others that are obviously named after other scientists. There's an
Frank.
Einsteinium. France. That's France. Yeah.
Mendelevium.
Mendelevium. Yeah.
Nobelium. Vibranium.
Lawrencium. Yeah.
Nobelium.
Curium.
I like Neptunium. I think that one's fun.
I don't know.
And proactinium. That proactinium reminds me of like maybe you use it for your skin. No, I don't know. It sounds like that proactive. Yeah, that proactive stuff.
Tennessee.
So here's your octet. Cole. Cole.
There's
There's like
that-
quick side conversations. It's like all anybody can hear on there.
Is
So.
it Tennessee?
Yeah, there's all kinds of ones, aren't there?
Doesn't matter.
Yeah.
Obviously, that was California.
That one just
Is
birds.
there California? it's fun. Some of them are really interesting.
Berkelium.
I like livermorium. Livermorium.
Berkeley.
Livermorium is
Livermorium.
interesting to me. See number 116, livermorium. Do you know what livor mortis is?
Rigor mortis?
No, liver mortis.
I thought rigor mortis.
So it's similar. Okay, so it's similar. So when you hear it, like, do you know what lividity is?
Livid.
Lividity, like,
You're livid.
no. So lividity has to do with like where blood pools. So liver mortis is like if you're doing like if you're a forensic pathologist and you're doing an autopsy, liver mortis would be like where the blood pooled, like when the body died. So like say you were laying on your left side, you would expect to see like dark blue,
Yeah.
you know, where blood pooled on that. That's liver mortis. So that's I always think, why did you name it livermorium? Because it sounds like that's what it sounds like to me. Yeah. So your octet rule, your noble gases are unlike any other group because of elements, of group of elements on the table, because of their extreme stability. They're noble, they're fancy, they don't need friends, right?
Wait, that's the octet. I said that the octet rule as
It is. Yeah, you're right. I'm just giving you some big points on it here.
Oh, I see.
Yeah, no, you got it. I know you have it right over there. So each noble gas has 8 valence electrons, except for helium, which has 2, right? These are just your big points for your octet rule. And the modern model of how atoms react to form compounds is based on the fact that the stability of a noble gas results from the arrangement of its valence electrons. So that is the octet rule in a nutshell. And I have my friend Homer, woohoo, 8 valence electrons. But I have a better one than that. I have a better one than that even. I have this one. If I had 8 valence electrons, I would be so happy. So, y'all, I was so punchy this week. Such a rough week. So it was
I'll be like Vanna White, and every once in a time someone says like,
Yeah.
like Dave, I'll just be like, ding.
ding. Yeah. So, okay. Ions of, does anybody have anything different for octet rule? How'd you state it? Abby, what'd you write? You wrote the thing directly from the book, right?
Yeah, a concept of chemical bonding theory that is based on the assumption that atoms tend to have either empty valence shells or full valence shells of 8 electrons.
Perfect. That is spot on. Absolutely perfect. So 8's your lucky number to remember. And if you look, you can, I mean, look at the, who's good at math? 10, 18, 36, 54, 86. What do these have in common?
They're all
There you go. Yeah. Mhm.
they're all
Wait,
even.
no, they're not.
They're multiples of 8.
No, they're not
plus
exact-
2.
They're not all just like, yeah, exactly.
It's not a multiple.
It's not, it's, I knew where they're going with
Some of them are
it.
multiples of 8, some of them are
Eight
multiples of 8 plus 2.
Plus 2. So the
Yeah,
first one,
starting from 2.
starting from neon. So when you look at the 2, it's just 2. And the 10 would be 8 minus the 2 from the previous shell. So if you remember that each shell, each period is a new shell, right? So you can do the math and say in the first shell, there's 2. In the second shell, there's 8. In the third shell, there's,
It's 18, right?
it's 18 minus 10. So it's 8. The next one is 36. So it's 8 again, because you would have had 8. Yes, because you would have had, it's not going to be 18. There's going to be other, remember the subshell thing? So yeah, but that's where you're headed. You're headed towards having 8 in your outer shell. All right, so ions of calcium, fluorine, magnesium, Michael's lost, and iodine have electron configuration. It's not like chop. But if you look at the configurations, like if you're looking at the shells with those numbers in mind, it makes sense. You kind of have to look at them. I should have put one up.
It's just
Yeah. So ions of calcium, fluorine, magnesium, and iodide have electron configurations which are similar to which noble gases? Okay, so calcium is going to be similar to what?
Argon.
There you go. Magnesium is going to be similar to,
Neon.
right. How about fluorine?
Neon.
Okay, now wait, somebody raised their hand that hasn't answered yet. And what's iodine going to be nearest? You've answered every one of them. Jeff,
Exion?
Xenon. Yep. Yep. No, it's kind of like the name that Elon Musk gave his kid. I don't know how. Yeah, Xenon. What is it? Isn't it?
There's some reporter who comes up
Oh,
and
yeah.
he asks him how the actually the 12 doing, and he goes, huh? Oh, you mean my kid?
Yeah. Yeah.
And then he says, that sounds like a password.
Yeah. It's crazy. Did y'all see what he named his kid? It's some unreal thing with.
Like AX.
Hey, I'm not complaining. The man's gonna send me to space. It's gonna be.
Yeah.
That's all good.
I'm not gonna complain about.
It's all good.
Apparently, if you like decode it in Latin, it actually means like tile.
Yeah.
It's a really cool game.
Yeah.
So explain why somebody raise their hand. Tell me why the properties of ions differ from those of their parent atoms. Somebody who's not Abby. Abby, I know, has the answers over there. Alex, you want to go?
Different amounts of valence electrons.
Okay, there you go. Anybody have anything to add or change?
They have one less.
One less left turn.
One less or one more, or two more, or two less? Right. Right, so they have different electron configurations than their parents. So they act more like atoms with the same electron configuration. Then they do their parent atoms. So that's saying sodium ion is going to act more like neon than sodium, right? And bromine is going to act more like krypton than bromine. That makes sense? Plutonium. No, stay out of the middle. We're only on the edges. All right, why do the atoms of metals form cations?
Because it's always,
Because they lose.
Michael?
because it's always easier with metals to lose electrons.
Right, if you look at the alkali and alkaline earth metals, it's going to be easier to lose electrons, which means they're going to become more positive, so they're going to be cations. Yes, all right, so that's how they get to their noble gas configuration. And how about the other way around? How about the nonmetals over here?
It's easier for non-metals to gain.
To gain electrons, which makes them more negative, so they become
It's easier.
not cations, but
Anions.
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 Ding, ding, ding. You can't read your own handwriting. Yeah, that's a thing. Yeah, that's the thing.
What about
See,
carbon?
I
It's
got-
easier to gain or lose with carbon.
So carbon,
Is a special case.
Yeah,
yeah.
that's what I thought.
Yeah, I mean, if you look at the way,
Special case.
see the color change there?
Yeah.
Yeah, anytime there's a color change yeah, you're gonna see exactly.
Polyatomic non-metal.
Because that one's kind of right in the middle, right? You're
Yeah.
saying? Yeah. That's why we're starting with the easy ones on the outsides, because they get more complicated. Carbon combines with lots of things, but it doesn't typically make these ionic compounds like we're looking at now. It makes more covalent. It deals with more molecular compounds. You're going to find carbon in, remember last week we did the schnapps thing? You're going to find carbon in all the biological molecules. Yes, Shannon.
How in the world do you say number 111?
111.
Rowan.
Oh, yeah. I don't think I've ever had to say that out loud.
Rowan's
We
getting.
don't even
Virginia?
know what it does, so it's.
Virginia? Yeah.
T-G-E-N-I-U.
What you think?
Can
What's
I
up?
tell a quick story about how bad my handwriting is?
Sure.
So I literally had to write his signature.
Nice.
So I went into this
My
smoothie
gosh.
place to get me and my dad a smoothie. And
Your own signature.
I'm like trying to write it. And she's like, oh, you can just write a line. I wrote a line and there was a dip in it. So I can't actually write a straight line. That's how bad my handwriting is. I'm like, whoop.
So if you're one of these people who can type and then actually learn from typing what you're like taking notes and typing at the same time, some people can do that. They can sit in a meeting
Yeah.
and they can type and remember what they've typed. Other people have a harder time with that. It needs to be the hand brain. I can't do, I've tried typing at a meeting and I'm a bad typist, but I can't, even if I were a good typist, it does nothing. I don't remember what I typed. But if I write it, I can close my eyes and remember exactly on the page where I wrote it. You know, I can see it in my head. I'm like, oh, I put that here and I doodled a flower next to it because I was bored for 10 minutes, that kind of thing. But that if you decide to handwrite, when you get to classes that require a lot of note taking, you'll develop shorthand because you won't be able to read it otherwise because you're just writing too fast. Like you'll develop your own little abbreviations for things. If I look back at my college notebooks, they're full of little abbreviations for things because I knew what it meant. I wasn't about to waste my time writing the whole word and then make it illegible.
I do that.
So this is a good one. There's your sodium. And what does your sodium have? wants to get rid of that electron, right? And give it to chlorine.
That poor electron.
Just take it, please. Don't mind
Take
if
my
I
child.
do. I know.
That poor electron.
That poor electron. She just wants to get rid of it. So
Stalker.
the arrangement of ion and sodium chloride shows that each ion is surrounded by blank oppositely charged ions. Ooh, who has?
No, number one.
Number one on the next,
Other
yeah.
element in the reaction.
Mm-hmm.
Yeah.
Anybody have?
Number
Abby
six,
says
short one.
6. Abby's right. Explain. Everybody's like, ah.
Oh, that's why, yeah.
Wait, what did you say?
I honestly, I
That's
feel
what the
like it
question,
had
we couldn't
something to
understand what
do
the question
with
was
each
really
of them.
asking.
Like one of them had 2 and one of them had 3, but then you had to.
Yeah.
I knew
So
when I was writing it down. I
when
knew
you're
what
writing it, it
meant.
made sense. All right. So
Blank
that
amount of opposite. So we didn't know it was asking for amount. We thought it was just asking for like sodium chloride. It has it would have 1 sodium and then a bunch of chlorine around it.
right.
So that's
So-
we thought it was just acting. Well, what would it have around it?
Yeah, I
Not
think
how
it
much
had.
would have.
Yeah.
We weren't looking for the amount.
Okay. So then the attractive force between sodium ions and chlorine ions results in an arrangement of ions in repeating units arranged to form what? What do we call it? Yeah.
Salt.
We say, well, it does form a salt, but what do we call the pattern?
Oh, the crystal. Yeah.
It's a crystal lattice. Okay, so this is the thing about ionic compounds. When we were talking up there in lab about how there are certain characteristics, and one of them is the very high melting and boiling point. Another one is that they form crystals. Now, not every crystal is going to be an ionic compound,
Yeah.
but ionic compounds are typically going to be crystals. Now, we had 2 sets of crystals up there, 2 or 3 sets of crystals up there today. We had potassium chloride and sodium chloride, which were both crystals and ionic, but then we also had sucrose,
Yeah.
which is sugar, and that's molecular. Those are covalent.
What
So-
about sulfur? Would that form any crystals?
That was just a straight up sulfur element as it was. It wasn't combined with anything.
Sulfur brick.
Sulfur brick, sulfur blah. And it didn't even dissolve, right? It was not soluble in the water and didn't do much of anything. It smelled terrible. So the sodium chloride crystal arrangement, so this is where the 6 is coming from, is talking about how they are arranged. And I think there was a graphic that showed you, wasn't there? I think that may have been where
Yeah,
Abby was looking.
I'm pretty sure.
Yeah, somewhere right in here. Where was it? Oh, wait, oh, I see it. It was right there. No, that's not it either. It was somewhere in here. I'll find it. So the sodium chloride crystal arrangement, the net effect is that what between oppositely charged ions is greater than, what do we have? Who has that one? Who has 3? Who is not? Abby has 3. Abby has done all her work. Michael, what'd you get?
In the sodium chloride crystal arrangement, the net effect is that the pull between oppositely charged ions is significantly greater than the pull between ions of like.
Yeah, pull or attraction. Attraction, repulsion. You could do it that way. So like charged ions are not going to pull. They're going to repel, right?
Yeah.
There's going to be repulsion between like charges and attraction between opposite charges. Because opposites attract.
But you shouldn't put attraction and blank.
Attraction and repulsion.
You shouldn't put that because then it's the powerful. Is it the same? So
So
a
this.
like
Mhm.
a like ion will push away just
Mhm.
as much as it will pull with another one.
Mm,
By putting two
the
different
net
things, let's say
effect, well, the net effect it's saying is that the attraction between oppositely charged is greater than the repulsion between like ions. And if you think about it, just kind of in general, like we were talking, like electron shielding. I'm trying to see if we can think of it in the context of that. But you've got the attraction pulling all those electrons towards the nucleus of the atom is greater than the repelling force keeping the even the electrons within that atom apart. Otherwise, they would push each other so far apart that there wouldn't be any atom because the electrons would just fly away, right? Because they're repelling each other, but they're also being pulled. And the pull is greater than the push, if we can think of it that way. All right, so the arrangement of cations and anions depends on what and what? Yes, Shannon?
The nucleus and the electrons.
Yeah, the size. Yeah, okay, size or nucleus, that's what you're going for. And then the ratio of the ions too. Okay, so ratio kind of makes sense there. So
Charge.
yeah, how many positives to how many negatives, basically. That's your ratio, right?
Yeah.
Good, okay. And I like this cartoon too.
So
Maybe
yeah,
this will
charge
help
is
you
the same as-
remember. Ta-da! This is a salt. This,
Yeah.
Because it's salt.
yeah, it's because
You
it's
get it
salt.
It looks
Yeah.
salty.
I think Michael needs the
Sodium
joke
is a
explained to
salt,
him.
obviously.
I
Sodium
don't think
chloride.
Michael
Salt
gets
is
it.
being
This is
salted.
a salt. She's dragging him off because
It's
she
not
really
a
wants
salt.
to be with him,
It's just dry.
apparently.
Isn't that battery? or something?
I think
No.
Physical battery.
No, I think that's a salt because there's
that would be a salt and battery.
extensive touching involved here. She's dragging him away.
And
She's
it's
tough.
expensive.
So anyway,
I think it needs explained more.
we need to explain this to you,
I
Michael.
think we need to get the police. involved.
I think you might be so illegal.
There we go. So the specific way in which atoms are arranged in an ionic compound is called what?
Crystal.
There we go. All right, and then the simplest repeating unit of the crystal structure is what?
I think that's the
Unit
unit cell.
That's the what?
Unit cell.
Yeah, there you go.
Yes.
Unit cell. Good. All right.
Yeah.
And then, so what is a compound that results when an ionic bond is formed between a cation and an anion?
Salt.
Salt. Yes. Okay, good. There it was. This is a salt. So when 1 mole of a salt is formed from gaseous ions, what's released? There you go. Yeah, lattice energy. That's totally not centered. There you go. All right, so somebody take number 9 for me. Somebody briefly describe why the structure of ionic compounds causes compounds to be hard. Yes.
Isn't that just?
Oh my
Oh,
gosh.
this
Cole-
was.
Cole
okay.
is so happy at this one.
I forgot about that. Yeah. It's just because of because they opposites attract.
Mhm.
They attract so strongly, it creates such a strong bond. That's
Right.
Really how it is, but I kind of got this on accident. I didn't even mean to. Yeah.
Okay. So I want you to visualize for a
I made a
minute.
joke and it
Have you
kinda
seen the way connects click together? Or what else is there? There's some other toys like that that are more like the ball and pin kind, where you can put multiple pieces together versus Legos. You ever taken like 5 or 6 Legos that are jammed together really hard, dropped them on the floor, and they don't even come apart? That's the same thing. You think about how they interlock. That's exactly what happens with ionic compounds. So they're they're locked together because they make this nice little lattice. And there's actually a picture.
And that's why they're not good conductors.
Yeah. When they're properly aligned, they're very difficult to break. So there's salt. That's what sodium chloride looks like. So when you go comparing that to sugar, for example, which will be next week's lab, they are completely different looking. Now we don't call these molecules. We technically call covalently bonded substances molecules. But
They're not molecules because they don't
Space now.
mix molecule to molecule. They're one big group of molecules. all
well,
mixed
just
together.
in general, the ionic compounds, they don't refer to as molecules. But if you see, I'll show you when we get to it, there's another term. But if you see how nicely that's locked together, does it remind you of how Legos lock together? Yeah, and then when we start dealing with other types of structure, when we deal with molecular structure, and you've seen them before, there's like a ring here and then like an arm and then a thing that goes this way and that way. And yeah, I mean, that's how sugar looks. Sugar is crazy looking. Like it doesn't look anything like this. So it'll make sense when you see next week's lab why.
So it's all nice and ordered.
Yeah.
Just
Exactly.
should be like.
So when a
So
force is
let's see.
applied, now I want you to look back at this picture for a second. Keep that in your head for the next question, okay? When a force is applied to an ionic compound and the ions are repositioned so that like charge ions are located next to each other, what happens to it?
The like charges will repel each other and the layers will split apart.
Yeah. So when you break a salt crystal, is it ever going to break into little round balls, or is it always going to make nice little blocks? I mean, that's the point. If you break something that looks like this, it's going to have, do you remember when we did earth science and we talked about mineral cleavage? Like, did it break smoothly? Do you remember?
Yeah.
I know,
Yeah.
you gotta go there.
I-
But it breaks smoothly,
Yeah.
right? So that's the whole point. If you break this, it's gonna break right down those lines. Wherever you've got repulsion, you put pressure on it, things shift around, you're gonna get some repulsion, it's gonna crack right down those lines nice and smoothly. Whereas some other substances are not gonna do that. So how is your ionic bond formed? I think we've said that like 50 times. There's your attraction of cations and anions. They want to party. There you go. So a salt is, yes, you have it?
No, I do
Oh.
not. I just want to say that.
The
Ozzy
straight
sunbathing
definition
is
from the
cute.
book.
Ozzy, what? What do you think?
Ozzy is sunbathing. is
Oh, yeah, he loves it.
Yeah.
But he gets so hot, like his coat's black, so he gets so hot, and then he comes in and it's like you touch him. And it's like getting into a hot black car.
That
You know?
happened when I was playing Little League once because we were the Orioles, so our uniforms were black.
Oh,
and
yeah.
We were literally just like dying.
Yeah.
Why would they make them black?
Because that's the team
Team
color.
colors,
And then
ugh.
they were trademarked. We couldn't change them.
True.
Because that was.
So who can define salt for me?
I can define salt.
I can
Huh?
also do it.
One of y'all.
Cole, you can do it.
Salt. Anybody have salt? No? Do you have salt, Shannon?
I don't have salt.
Wait,
Don't make
salt?
you can read it. You can
Define
read it.
salt.
Yeah.
It's in the book. It said definition of salt in the book.
I know it did, but I didn't.
All right,
do the
Shannon, what you
book.
got?
I Google.
Wait,
Oh,
isn't it
Jesus.
that's what we just did? Just define salt.
Pretty much.
Okay.
Salt.
So salt is a compound that results when an ionic bond is formed between a cation and anion.
Right, a girl. Check it out. Yep. And there's one other thing a salt is, which we haven't really gotten to yet. It's also a product in an acid-base reaction. So when we start doing acid-base reactions, you're gonna find salts again. And since you understand, y'all, since you understand how a salt is formed with these two groups here, right? It's gonna make more sense when we get to acid-base reaction, how you end up with a salt every time. Alrighty, so whew, that's the same. Oh, look at that. How'd that get in there twice? Okay. So then we have types of bonds. Now we'll get to covalent later, but here's our ionic, and it, take this and be mine, because this isn't sharing, this is taking, right? There's a whole concept of sharing electrons versus taking and giving. So this is taking and giving as opposed to sharing, which we'll get to when we get to covalent. I like them. He's giving her a little tiny electron. She looks really excited about it. She seems much nicer than the one that was dragging away the other guy, right? I mean, I kind of worry about that. So why do ionic compounds have high melting points and high boiling points? Cole, you were saying it earlier. Go ahead.
So because ionic compounds bond so strongly, it takes breaking apart the bonds to melt them. This task is difficult because they cannot be in fixed locations.
Yeah, okay, so exactly, that's what we're dealing with here. So they're very, very strong bonds. So think about those Legos again, stuck together.
You ever got like the half Legos that are 2 pieces long?
Are you
The ones
asking
are
me
2
that
pieces
like
long,
for
you stick
real?
them together and you gotta break them apart. You don't have the tool either. And then even if you have the tool, you can't like stick it against anything.
This summer,
Ridiculous.
I sorted how many thousand Legos? Like if y'all haven't seen our Lego collection, it is nice now because I sorted bins and bins and bins, and we gave away lots, sold a ton of Legos. We sold a ton of Legos. But anyway, so I know all about taking Legos apart. But imagine you're you ever done the sticks and marshmallows? You could build something that is pretty much the same structure as Legos, but one of them is going to take very little energy to just, whereas the other one, you're going to have to really work to pop them all apart. So this is the same thing with breaking as it is with your high melting points and high boiling points. So also think if you had your marshmallow and toothpick structure or whatever, and you pushed it, it might give a little and come back, right? There might be some malleability there. Whereas if you were to put force on your Legos, they're either going to move or break, right? They're not going to bend very much. I mean, Legos have bend a tiny
Unless
bit.
it's like a technical thing, which gets
Yeah. They'll bend a tiny bit, but these things don't. So this is why when we talk about ionic compounds being really brittle, right? They just shatter as opposed to some things which have a little give. So Michael, why are they generally poor conductors of electricity in solid form?
Because when they're solid, they cannot move freely. To be able to move is you need to be able to get the charge from one to the other by
Right.
them bouncing into each other. And when they're solid, they have the strongest bond, so it's very hard to take it apart
right.
To shoot them between the two.
Exactly. All those little electrons are locked in because they're all doing a job, right? They're all connecting one atom to another atom, and they don't have the ability to get out and be used. When you look at the way metal, just like a pure metal works, and you see the way atoms, for example, all join together, you'll see that they allow for the electrons to flow. Whereas in this case, there's no flowing because they're all committed to their job. They're all locked in and they don't move freely. Now, when we put them in water, what happened?
They have the ability to move freely.
Yeah, they're dissolved. So
Yeah,
the bonds are
so
not
if
as
you
strong, so you're able to move them.
Yeah, so you have to think about, and this is something you have to keep in mind for next week. So you've got your ionic bonds, right, that are, you got your one unit, your one sodium and your one chloride, they're together. But you've also got billions of others, right, that are also locked to that one. So you have to think about the difference between the compound as a whole, the substance as a whole, and then the compound like as a unit, right? So when we put it in water, we had all those billions of units and we separated them. That can be done, but if you're going to separate them to the point where you're going to like completely break them apart, like melting them would be, or boiling them would be, because it's changing the state. Because in that solution, we had solids, right? We didn't really change this. We didn't change the state of the sodium chloride when we put it in the water. We can't see those solids anymore, but they're still in there, right? It's just particulate. It's tiny, but it's in there. So if you're going to actually change its state by melting it or boiling it, it's going to take a lot of energy to break it apart. So when are salts excellent conductors of electricity? Everybody should know this because we just did it.
Salt.
Yeah, we put it in a solution, right? In a liquid state or in a solution. You knocked my Roscoe off the wall, Michael, with your big hands. There we go. Almost. There we go.
I'm not like triggering OCD with that. It's good.
Can you believe it's been a year for those of you who were here last year? It's been just a little bit over a year since we lost him. That's just crazy to me. It didn't feel like that long, but yeah.
Michael Dalton.
Yeah, I had to warn everybody last year because I had to warn everybody and sent an email to everybody. I'm like, we're gonna lose Roscoe on Monday and classes on Tuesday. I don't want anybody walking to be like, where's the dog? And then we'll have to explain it. We're already all upset. So yeah. So then here's a question. Why do we salt the roads in winter?
Because it
Ooh,
interferes
Shannon.
freezing. Because it helps with the ice and helps with the grip on the tires.
That's part of it.
It helps melt the ice.
So what did we just say about their melting and boiling points of ionic
Very
compounds?
high.
Oh, they lowered. They raised the freezing temperature.
Yeah, so if your
So
melting
it's harder to
point
reach it.
is going up, your boiling point is going up, then also your freezing point is going
Oh.
right. So if you put salt on the road,
It's horrible for your car. though.
it's really bad for your car. But if you put salt on the road, your what are you doing?
I think that's.
Yes.
That's like the scene from Ant-Man and the
Oh,
Wasp.
yeah.
Louis is like, what are you doing guys want? You know, that's where like our slowly like sister stays, and like then all the fancy southern guy comes in and it's like, yeah, he's right. And like, what do you know so much about like car wash, like rent it? And you're like, yeah, I like
So
it. I don't know where I was going with
that was
but-
interesting.
I
So
know, yeah,
what
the
happens
icing
then
road.
if you turn the water on the road into a salt water solution? Which is what happens. It's got to get much colder.
That's why the oceans don't.
Right,
freeze and
right.
lakes and rivers will.
So your freezing point is lower, right? Lower. We think we said higher a minute ago, but lower. Freezing point's lower. So if you're gonna put your water freezes at 32 Fahrenheit, it's gonna freeze at a lot lower temperature if it's now sodium chloride solution or whatever they're using, magnesium chloride, I don't know what they're using, something on the roads. And so therefore, it's got to get a lot colder to make ice. So it's going to make the roads more slushy, hopefully, and not like ice. Of course, the problem we have here is we have a compounded problem here. So we don't get snow like they do in the north because their ground gets nice and cold. So when the snow hits it, it's snow.
Yeah.
But our ground doesn't get that cold typically. So when the snow hits it, it melts. And then
You just
It keeps snowing and it packs it down.
it
and
keeps
packs it
snowing,
down.
which super cools
And
the
those
little
ice
layer
storms
of
and
water
stuff.
on top of the asphalt. And then you get
And
ice.
then you get to go drifting, even if you.
Yeah. And you get ice that gets compacted by every set of tires that
Even
runs
if you're
over
You
in
it.
just
it's
jinxed
not a
us.
drift
Now we're gonna
field,
have the
you get to
coolest
do it
winter
anyway.
we've had in 100 years.
Well,
I
it's
hope.
that's why like when like all of my Yankee friends are laughing at us, they're like, you got a quarter inch and you can't drive. I'm like, it's not snow, it's ice.
It's snow.
Nobody can drive on this. Then we have the problem of snowplows and salt trucks, which what was it? The year we had the big snowmageddon, didn't Forsyth County have 1 or 2?
No, like the city of Atlanta, I think had like, was it like 6 trucks.
And they had to
that whole
loan
city.
them out to the surrounding metropolitan
So after that,
areas
They bought a
because
fleet of them, I think, yeah.
yeah, we
And
just
then
don't
it
have
hasn't
them.
snowed like that since.
It's
only
not
that, but,
cost
like, the salt
effective.
and stuff will like, it'll get up and build up under your car and it can cause the rust to pass.
So they tend to
and
mix-
stuff, yeah.
So back to what you were saying about traction, they tend to mix sand with it. So very often it's sandy brine. It's
Well,
like salt water full of sand. It's beautiful.
Well, when Dad, Drew and I went on the Colorado trip, we rented a black Chevy Tahoe, and there were some salt trucks in front of us on the way back. And when we pulled into the airport, like the whole car was just completely dirty.
Oh yeah,
Yeah.
Like,
yeah.
Cause there was salt and muddy stuff all over it. Yeah.
It's pretty gross. Yep. So here's another one for you. Ionic compounds. All right. What are our characteristics of ionic compounds? Anybody?
I am.
Why don't you give one, Abby?
They're solid at room temperature.
Okay. Jack, you give one.
They form crystals.
Okay, cool.
High boiling points,
Mhm.
boiling
I love
points.
boiling.
I love
Mhm.
It's fun.
Michael, what have you got?
Bad conductors and
sucks.
solid and good conductors and liquids.
There you go. All right. And did we miss one?
Oh yeah, and they have.
Hard and brittle?
They
Yeah.
do not consist of molecules.
Yeah, so solids at room temperature, hard and brittle, do not conduct electricity in solid form. We saw that today when we stuck the little thingy in the pile of salt and nothing happened. And then we have excellent conductors of electricity in liquid or solution form, high boiling and melting points. All right, so here's some, those result in very strong bonds. So it was asking like, how does that relate to the bonds? Very strong bonds, right? So here are some other little slides with some images, just to kind of help you get in your head. Salt crystals form in repetitive geometric arrangements. So always your repetitive geometric arrangements. That's halite right there.
Yeah.
Very pretty. Little chunks, big chunks. So with your ionic compound here, you've got your metal and your non-metal. And your metal is giving an electron to your non-metal to get an ionic compound, and it makes a smiley face. Isn't that cute? I didn't even see that at first. It's smiling. Yes.
I have one thing to say, and it is science related because
Yeah,
Mike, you guys-
meteorology.
Michael,
Okay.
Do you need me
Can
to
you
explain
believe
it
we
to you?
ran out of names for like
Hang on.
hurricanes?
Yeah.
Wait. What?
I couldn't believe that we ran out of names for hurricanes.
Yeah.
Like, I thought that list just went on for like ever and like never
I went to
stopped.
beta now.
They've
It's
got
now
an
it's
A
Delta.
through
Is
Z
it
for
Delta?
every year, and then they start over again. And it's interesting, they've added, like the last couple years, they've started adding like more diverse names to it,
Yeah.
which is really kind of cool because
Antonia or something
yeah,
like
it used to be like all very like Eurocentric, pretty much English names, and now it's very, very Anglo names, and now they've gotten all kinds
What
of
kind of name
cultures.
is
and
Delta?
what kind of name is Delta? Yeah, there you go.
Sure, name like the
Greek alphabet now.
Hey, now there's an actress named Delta Burke. There you go.
Imagine
So
seeing a
they're-
hurricane, imagine seeing a hurricane,
He's
deep
Delta
hurricane
Burke.
shark.
She's an actress from way back in the day, Are you guys good?
Yeah.
All right.
Hurricane Becky.
So you got your form by metal and a non-metal.
And then you get your-
All right, now what's this one? I want you guys to tell me what these are saying from now on. Tell me what I'm trying to tell you. I'm communicating something through this image.
So, because when they're solids in a shaker, they're not going to conduct very much. And
So,
when
oh,
they're
they're
mixing with
liquid,
water,
they're
it's
solid
in a
into
cup,
a
they're
glass.
going to be a good conductor.
Conduct.
Right, so
Salt.
solids, they don't conduct, but in a solution, they do. Look, I made that for you. Isn't that cute? So there you go. Poor conductors of electricity in solid form, excellent conductors in liquid state or in a solution.
Yeah, no.
All right. What's this one?
That's a crystal.
Crystal.
It's a crystal.
Of course you know. Yeah.
Amethyst.
It is, well, it might,
That's
yeah,
a
that's not
crystal.
actually, that one's probably not actually an ionic compound, but you get the point, it's crystals.
Go sell that to your partners.
So they have a, they have a crystalline structure, high boiling point, high melting point. All right, what am I, what am I, hey, guys, what am I telling you here?
How they're formed. A cation and an anion.
Opposites attract.
There you go. Yeah, look, so there you go. And I'm also telling you that the small, okay, so here's your term. The smallest unit of the ionic compound is the ion. Ionic compounds don't have molecules, they have formula units, which represent the smallest whole number ratio of ions. So if your chemical compound is NaCl, then your ratio is 1:1, 1 sodium to 1
Yes.
fluoride, right? All right, so then, and what's this one telling you?
They shatter.
Yeah, they're hard and
Easily.
brittle. Yeah, brittle solids.
Which one is that, Abby?
There's no one for you. Ah, it's always sodium and chloride.
The metals give away.
Give up electrons and the non-metals take them.
Although I'm not sure where they get little baseball gloves and hats and their
Tiny
size.
atomic size, yes.
Hey, hey.
So having equal
Academy
amounts.
sports and outdoors is everywhere now.
Yes,
right?
but
Maybe
at
true.
the subatomic level, at the atomic level.
All right, so on to the next ones. Having equal amounts of positive and negative charges is called,
Electron neutrality.
yes, there she goes, electroneutrality. All right. An electrically charged group of 2 or more bonded atoms that functions as a single ion is called,
Polyatomic.
yes, polyatomic ion. Collections of what?
Cation.
Cations are never found without similar number of anions or sometimes electrons nearby to effectively neutralize their charges. All right, the names for what?
No.
Ions?
Roman numerals, right?
Cations, yeah, come from the element from which they are formed. So cations, remember, are your metals. So when we say sodium chloride, we say sodium, right?
Mhm.
So that's the name for the cation, comes from the element from which it's formed. When element forms 2 or more positive ions, the ions are distinguished by using what?
Roman numerals.
Roman numerals to indicate their charges, right?
Falcons can actually win a game this year.
Did you see there's a meme going around that says, we're in the fourth quarter of
Quarter
2020, I hope we're playing the Falcons. Me too.
I'm still holding out hope
Oh my.
October hasn't been so bad.
that we can
The
actually.
name of a simple anion is formed by changing the ending of the element name to ide, right? So sodium chloride. All right. Blank is a whole number written below and to the right of an element symbol.
Subscript.
Yep, subscript. What do you call it when it's above?
True.
Superscript.
Yes, superscript.
Oh.
Any chemical compound that is composed of oppositely charged ions is called what?
Ion.
There you go, ionic compound. All right, so now we get tricky.
Okay.
What do
wait,
we
we
have
weren't
for the
tricky
first
before.
one?
KBR.
Yeah.
That's KBr, potassium bromide. All right, somebody read what's the next one?
Base.
Barium fluoride.
I know.
Barium
Bath.
fluoride. Looks like this. Do we see it?
No, base.
You'll beef. Do you even bake?
Why do we have 2?
I don't know. We should.
Where's the 2 come from?
Because
Subscript.
barium
just
needs
wants
to
to
give
be
up
extra.
2 and fluorine can only take 1.
Barium needs to give up 2 and fluorine can only take,
It's the number of
one.
atoms in the formula.
so we need 2 fluorine. There we go. All right, so the next one is going to be tin 4 oxide, right? And that looks like
Hello.
And oh,
SN is tin,
What do you mean? How did you get that?
I just wrote the wrong.
SNO2. So where's tin?
Don't you have to put the 4
What?
plus?
50.
50, okay. So SN, and how many, yeah,
Would you not put the 4 plus above as a superscript on a 2? Did I read that somewhere?
the 4 plus on the where? Wait, on the 2. No, okay, because this is the, it goes back to this question, right? Whoop, whoop. Right here. when an element, not elephant, forms two or more positive ions.
The elephant.
The ions are distinguished using Roman numerals. So if you look at 10, which is 50, it needs to gain, it could gain 1, 2, 3, 4. So because it can gain 4, it can become four positive ions. Am I making sense? I'm not making sense.
Yeah.
Okay, sort of making sense. All right, hang on, go back.
Why we needed that then.
All right, so the next one was cesium bromide.
Yes.
Cole, what'd you get?
CISPR.
CISPR, CSPR, like that.
Guys, make
Because
sure you're.
cesium's there,
That's
bromide's
CISPR.
here. Don't need to add anything to it. And the next one was cobalt to bromide. Where's cobalt? Cobalt to
27.
27 is cobalt. And then,
Wait, no, sorry, I was thinking,
It's okay.
I was thinking to myself. and I-
COBR2.
So it's COBR.
COBR
2.
I would say Cobra, but there's no way.
2. So
I said
Cobra.
cobalt is 27. Which group are we in?
Transition metals.
Right. So how many valence electrons does cobalt have?
Which one's cobalt?
Cobalt is 27.
27.
Mm-hmm. Ding. Oops, she left and came back. Do you
Nine.
see? It is, I'm double checking. Yeah, it's
Nine.
8.
8. Yeah.
No, 9. I'm 9. Sorry, 9. Yes. So yes.
So,
All right. How about the next one? The next one was mercury 1 sulfide.
HG2S.
Hg2s. And why do we need 2 mercury?
Because it says mercury Roman numeral
That's all there.
So where's mercury? 80.
1. Sure.
Remember, you guys have this one in the front. This, you guys have this,
80.
where is it? You guys have this periodic table in the front that, whoops, that has your groups written above it, right? So that's always a good place to look.
Yeah.
So mercury is in 12, right? And then what were we with? Mercury sulfide. Sulfur needs 1, 2 more. Mercury has 2 to get. You need 2 mercuries to fill the sulfide. We're going to be drawing it out a lot too. And truthfully, oh, sorry, I'm dropping things on the floor. Sulfur. I think that's yours. Just saw that it fell on the floor.
Jack, are you okay? You're
And
snapping.
then, what do we get for aluminum iodide? Aluminum iodide.
Wait.
They're just ALI3.
I3. How many spaces are there between AL and I? 1, 2, 3. Do we see it? 1, 2, 3. No. Going this way.
Oh, group?
How many groups? How many spaces?
3.
1, 2, 3. Okay. If you, sometimes it's easier to kind of draw the image. No.
AL to I, right?
How many are between AL and I?
In between.
Yes. All right. So names and formulas. All right. What is Cu plus? What's that one? Copper 1. Because it's got a plus. What's the next one? Cl negative.
Chloride 1.
Chloride. Yep. And we don't need to give it a 1 because it's a negative.
Yeah.
How about O2?
Oxide.
Oxide, O2 negative. Yep. Sorry. And then how about P3 negative?
Phosphide.
Phosphide. Good. And sodium with a
Ion.
plus.
And A plus.
Just sodium. Yep. Because we're just going to call those metals what they are, right? Okay. How about the magnesium with 2 plus?
Magnesium ion.
That's magnesium because it's, again, it's over here. Those just always just call them what they are, right? All right, and then you know the next one,
Sodium
chloride.
chloride.
absolutely. And what's the bottom one there at 22?
Zinc sulfide.
Zinc sulfide, good. All right, how about number 24?
Iron 3 oxide.
Iron 2 oxide.
Iron 3.
3.
Yeah,
Mhm.
iron 3 oxide.
Iron 3 oxide. So this has to do with how many, shoot. I'm gonna read it from here, so I don't have to go back. The name of the simple anion is formed by chain, no, not that one. Where did the Roman numeral one go?
When an element
oh, hold
forms 2 or more positive
Yep.
ions.
There you go. I wanted to read it exactly as it was. No, I
And it
lost it
has-
already. Which number was it, Michael? Oh, yeah, 5. When an element forms 2 or more positive ions, the ions are distinguished by using the Roman numerals to indicate the charge. So what can iron form? Where's iron?
Iron is 26 Fe, right in the middle of
Fe.
the blue,
Yep.
top row.
Okay. So what group is it?
Metals, or transition metals, sorry.
What number group is it? You can always look at that other one I gave you because everything's in it.
8.
8, yeah.
8. So
Yeah.
positive ions. What can it form for positive? So if you add 1, 2, now you're nothing, right? So here's the thing. If you add going this direction, okay, you're gonna add positive moving towards the right. So you,
Cobalt, 9, and then copper.
right, okay. So basically this has to do with which direction are you gonna go? So if it's gonna be a positive ion, it's going to lose electrons, right? Versus gain electrons. So these ones in the middle here, the ones on the outsides are pretty straightforward. The ones in the middle, so if you look at the iron, it had, what do we say, 8, all right? So it wants to have, and it's group 8, hold on, this is where I started to lose it this week, so.
How do you know it wants to have what?
Well, see, so there is, hold on. Let me come back to that. Let me get the rest of these answers and we'll check them and then I'll show you, okay? Because this is where lupus took over my head this week and I sat outside on the back deck for like 4 hours doing one slideshow because I couldn't think. So it's real fun. So what did you get for the next one then? MG3, magnesium nitride. Yep, nitride.
Huh?
I tried.
Mm-hmm.
I tried.
I tried.
What's nitride?
Yeah, and then
Oh, this is nitrate.
because we add the ide,
Well, I tried.
zinc oxide, and then what's next?
Sodium iodide.
Sodium iodide,
Copper 1 oxide.
copper 2.
Copper 2.
Copper 2. We're gonna do those in a minute.
Copper 2 oxide.
Yeah, copper 2 oxide,
Calcium chloride.
calcium chloride, good.
Chromium 3 chloride.
Chromium 3 chloride, good. How'd you know it was 3, or did you just look it up?
I can't remember how many, but we were able to
Okay.
piece together with the.
Okay,
In the book, they had a way to piece together the names.
right. And then
One table is what the
magnesium.
names meant, the formulas. and
That's the
names.
one I was gonna look at here. Yeah, when I get through. Yes.
Is there an element called? Huh? Oh.
Here you go.
All right, so next we're gonna come back. We're gonna,
Mercuric oxide.
yeah, we're gonna go over the hang on, we're gonna go over the middle ones in a minute. Yeah.
So I have a question.
Uh-huh.
What's the last one, for number 27? I
Yeah.
see that the back says iodide and this one
Mhm.
says iodine. Why is that?
The ice.
So it's
the-
because you
IDE
switch
is
it to
added
ide
in.
because it became, that's the name of the ion. So just like with sodium chloride, you name the metal and because that's your cation, and then your anion gets an ide. So
Okay.
so it's an iodide for that reason. Yeah. All right, so how are polyatomic salts names? That's what we've been doing. So your cation plus your anion, right? And then you get an ite or an 8. And this is where this little handy chart, if you haven't already studied it, this is where you should be looking at it. You get an ite or an 8, and that's based on what? That's based on whether or not it has, see, it'll tell you right here. You got your 8s all the way on this side, and that has to do with whether or not hydrogen is your first element. And then you got your 8s all the way on the other side. And then you get Theo for sulfur, right? Yes, sir.
How do you say, just out of curiosity, how do you say element 107?
Oh, boy. Oh, that's borium.
Thorium. Okay.
Like for Bohr model.
Yeah.
See, Rutherfordium, wherever it was, Rutherfordium and borium are not too far apart.
Sagittarius.
Yeah. How do the formulas for atomic salts relate to their names? And that's what we were just saying. Your cation plus your anion, right? And your cation is a metal and it's just going to be the name, right?
Yeah.
And your anion gets the I.
Yeah.
All right, so 34. What was our answer for 34?
B.
B. It's B.
Yeah. So your 8 and your 8 are endings of polyatomic ions containing oxygen. 35,
A.
one hydrogen, monohydrogen.
Yeah.
And then 36,
D.
right? 2 hydrogen. So what is, yeah, what is, you see it all the time. You see the, what is it, dihydrogen? Yeah, I was going there, but changed my mind. Different situation. All right, so how about the Theo? We said is where you have sulfur, right, as your anion. It's just special, I get. Okay, so here's the compound flow chart that I gave you in the front of your binder, okay? You just follow it along. So the place where you get stuck is it a transition metal, okay? So this is where we were when we were like, right? We have no trouble with this category, right? No, it's not a transition metal. We have no trouble with these. We kind of roll right through them. It's the transition metals that are stuck. So count the different elements. How many are in there? 1 or 2. 2 elements with a transitional metal and a non-metal makes it ionic binary. And then if it's 3 or more, makes it ionic ternary. And then here's where we're getting a little stuck. Name the transition metal first. Okay. And then determine the charge of the metal and write it as a Roman numeral after its name. Okay, so how do we determine the charge? Now I was looking in this book, that's not even
How
my book.
does charge change?
Where's
to
your book?
Roman numeral?
Oh, here it is. So yes, that's where we were stuck, is how do we determine the charge? So let's look at exactly what this will look at the same page. So that would be, anybody remember what page it was on?
Of what?
It was in your book.
Oh, no.
Of what?
There was a thing in your book about how to determine the charge, right?
I think it was like 170,
I'm
180.
looking.
170 or 80 was in there.
The whole lesson is around that.
Want to make sure
Yeah.
that we find it. So we're all looking at it
It
together.
was like 183 or something.
Looking. Okay, X-rays. Oh, here we go. It's in here. Okay, right here. Simple rules for naming. Oh, so simple. Okay, rules for naming simple ions. In the case of copper, okay, yep, it showed me that, but it's not showing me. I thought it had a graphic. Maybe I saw it somewhere else when I looked at all my stuff online. Determine the charge. Okay, well, let's see if we can find. I think your friend Professor Dave actually.
Yeah. Good old Professor Dave.
Professor Dave actually had a great video
My bud.
on this. What did you just do?
No, grabbed his cap and clicked it.
Because he's going to have it with graphics that I don't have in front of you. So it would be better, I think, to just look at what he has.
It's not right on. Why would you know?
Professor Dave explains.
I don't have it. Look.
Said that so you're like
Huh?
TikTok before?
Huh, maybe this one isn't him. I know he has one, though. Why did I leave? Wait a minute. Why did I leave? I meant to be in YouTube, though.
What about Professor Maeve?
I know Professor Dave has a whole big naming thing, but we already kind of looked at some of that. So
Like, Professor Maeve explains. Like,
Professor Dave explains. All right, let's see if, let me go back and screen share this.
Professor Maeve is Professor Dave's alter ego, where he does everything unscientifically and just speculates about everything.
All right, so let's see this. I know he has one, but it's long and it's all the stuff. It's the stuff that we partially have. So let's see here. If this is going to make it a little clearer. Oh, abolish the police. John Ossoff.
Oh, yeah, so John also.
You gotta love it. Okay, Cole, can you turn the volume up over there for me, please?
Yeah.
Thank you.
Professor Dave explains.
So much easier to look at the chart and have somebody not stumble about it. You got it? Okay. Yeah, that's pretty much, they all go like that. But you know what I noticed about him the last time he ran? He didn't blink in any of his ads. It was really disturbing.
He's lizard person.
Here we go.
Let's try this.
Transition methods.
Look at this.
So
Yep.
when we find the ionic charge, look for ionic charge, we often think of this pattern on the periodic table. One plus, two plus, and we skip the transition methods. That's what we're interested in this video. We skip them and we go 3 plus, 4 plus or minus, and 3 minus, 2 minus, 1 minus, 0. And that's very useful to understand the general trend for ionic charge on the periodic table. It's a bit of an oversimplification though. If we look at a more detailed periodic table, we'd see that
Let's just
we
make it
have
complicated.
one, they're all 1 plus, 2 plus. So here are the transition metals. We have these post-transition metals, some of these down here like lead. So this is a little more detailed, and you'll note that there's really no 4 plus or 4 minus on this table. So here we have 3 transition metals though, that always have the same ionic charge. Silver, 1 plus, and then zinc and cadmium, they're always 2 plus. But for the rest of them, some of these transition metals down here, we really don't know what the ionic charge is. To find it, we'll look and see what it's bonded to. So these are all positive. We'll see what they bond to here, and then we can work backwards to determine the ionic charge. So let's try, let's see how it looks. Let's try copper oxide. So copper transition metals right around here. We don't know its charge, but oxygen, oxygen right here has a 2 minus ionic charge. And this copper oxide right now, it's neutral. There's no plus or minus out here. So all the charges, they add up to 0. Net charge is 0.
That's
Oxygen,
plus 2.
2 minus. That means for them all to add up to 0, the copper has to be 2 plus. And that's its ionic charge.
So it'd be
Say
copper,
remain.
parentheses,
Copper
Roman numeral 2.
2.
They're gonna change that
And
to,
the 2 would be a Roman numeral in parentheses
Yeah.
after the word.
see, that's how
copper.
you were getting
So
there?
Copper 2 oxide here. Let's try another one, maybe a little more complicated.
That's great,
Wow.
thank you.
Fe2.
That's exactly what I wanted.
O3. This is a component of rust. So we don't know what iron is, it's a transition metal. But we do know again that oxygen has that 2 minus charge. So we'll put our 2 minus charge up here. And we know that all the charges on the Fe2O3 compound, they have to add up to 0. So 3 times 2 minus, that's 6 minus. So this part of the compound is 6 minus. So the question is,
Plus
to
3.
get 6 plus, what is the charge on the iron? 2 times something will give us 6 plus.
I'm so good at math.
2 times
CO.
6 plus. That'll give us 6 plus. These
So
are
it's
cancel
iron
out,
3
we'll add up to 0.
oxide.
So the ionic charge on the iron is 3 plus. We call this iron 3 oxide. And note that this 3 plus, there's 2 iron atoms, so each one is 3 plus. Now you try.
Yeah, so now you get the 6.
How about CuCl2?
Why couldn't you just say it's-
You got 2. How are we gonna get there?
CuCl2, again, copper, that's a transition metal right around here.
Plus
Chlorine,
2.
that's
Or
right here.
minus.
It's in group
Mhm.
17, sometimes called 7A. All of these
So
have
it's
the
a
1 minus ionic charge.
minus.
There's 1 minus up here. 2 times 1 minus, that's 2 minus. So the copper to have this 2 plus, so these add up to 0, has to be
Copper 2.
2 plus. Kind of imagine a 1 times 2 plus gives us a 2 plus. Net charge is 0. The charge on copper is 2 plus. We call it copper 2.
And I'll put this link in the email so you can look at it again.
Pause and try this one. So for Fe2S 3. It's
Okay,
pretty much
here's your
the same
S.
as Fe2O.
2 minus 3, right?
Overall, neutral compound, so we look up oxygen right there, 2 minus, 3 times 2 minus, so we get
6 minus
This has to be 6
6
plus
plus.
2 times 3
Mhm.
plus. That'll give us 6 plus. Net charge is
Great.
0. Iron 3
Or iron, sorry,
sulfide.
iron 3.
We'll
Yeah.
wrap up with one more. ZnCl2.
Okay.
Chloride.
There's the
So again,
chloride.
neutral compound, all the charges add up.
Minus
to
1.
0. Chlorine.
Plus
That's
times
right
2.
Here, that has that 1 minus. We have 2 of them, so 2 minus the zinc
2
has
plus.
to be 2 plus. But we also know zinc is an exception for the transition metals. It's always 2 plus. So we could have known that without figuring out the chlorine. If we name this compound, because zinc is always 2 plus, we can just call it zinc chloride. We don't have to call it zinc 2 chloride. It's just zinc chloride. This is Dr. B with the Ionic chart.
Thank you, Dr. B.
for Transition metals.
I like Professor Dave.
Professor Dave is fun. I like him.
Professor.
So- Then I wanted to show y'all, I got a list for you guys of actually some common ones that you may want to write down somewhere in your binder. Okay? So they are, I'm gonna put them up here, and these are the ions, okay? These are not compounds, these are just the ions. So if you are looking for, it's around because I don't want it to be backwards.
It's like doll.
Camera. No, I can't see now. I put a giant glare on it.
It's looking into the door, like into the reflection, like thinking about his existence. And like,
Just
what am I doing?
Okay, there we go.
Oh, did we turn in the homework?
Not yet. Hold on. Hold on. Yes, you're going to turn in the homework.
I did.
But yeah, put your homework in the folder up there. All right, I'm gonna write some for you guys, and this should be a good cheat sheet. You're gonna want to put these somewhere.
Why are you the way you are? I don't understand, you know?
Okay. All right. So basically, this is going to be,
Are you doing the names of the formula?
well, this is, okay, here's the name. And then here's,
Name.
I'm gonna be like this. This is kind of what you can call it. And then this is going to be like the, whoops, sorry. Okay, these are all just ions. Can you see a little better there? Okay. So copper 1 sometimes is referred to as cuprous,
Oh, yeah, I asked about that.
okay? And that's gonna be what? Cu. Okay,
What's a plus for?
well, because it's showing that it's a positive.
Okay.
It's a cation. Do you have something to write with? Are you good?
Oh, yeah. I'm good.
Okay, I just don't want you to lose it. It'll probably help you later. Copper 2 is cupric. And that one's gonna be what? Cu,
2 plus.
right? Cheat sheets are good. Iron 2 is ferrous, not as in Bueller, spelled differently. And that's Fe plus. Iron 3. Ferric.
Actually, a Ferris in those.
Huh?
Ferris.
Yeah, like you can find, sometimes they'll say, instead of saying like iron 3 oxide, they'd say ferrous oxide. And sometimes that, yeah, you'll see it
They make
for
Ferris
sure.
wheels.
What is that?
They make
3.
Ferris wheels.
There's a bunch of iron to shape in a wheel. There's your Ferris.
There you go, your ferrous wheel.
Ah.
All right, now we have lead 2. Does anybody want to guess what that one's gonna be? It's an us.
Why is that so pretty? Like,
I don't know, my handwriting usually stinks.
you turned cursive all of a sudden.
Is it 2?
Columbus, isn't that fun? That's why lead is PB.
Christopher Columbus.
Columbus, yeah.
Christopher Columbus.
And that is, and then we have
Hopefully
two,
I'll
right?
be able
Yeah.
to get these on the video because I have not been keeping up. I tried.
These are just common ones, so you may see them, you know?
Lead free,
Plumbic,
because there's lead pipe, lead,
I'll give you a second to write.
lead pipes.
Plumbers.
Plumbers do pipes.
Very good. Dun, dun, dun. For psychic people around here. Okay, so then we have Mercury.
Wait, is that bottom one a 3?
Oh,
I
4.
PV 3+.
And Mercury, where am I? Mercury 1. And very often these are like this, right? Usually they're like that.
I'm just gonna be squinting at the video.
Mercury. Mercury. I almost spell this one wrong if I'm not careful. Mercurus, and that is HG 2 2+.
I'm gonna take a picture.
Go for it. I'll post it too. And then we have Mercury 2. And that one is Mercuric. Mercuric. And that one is just HG 2+. So HG 2+, and then HG 2+. And there's
Mercury 2.
10, 2. And this one's fun.
Oh.
Stannis.
Stannis.
Not
Like
Thanos.
Stannis?
Not Thanos. Stannis.
Really not Thanos?
Not Thanos.
Man.
Stannis.
Like John Stanos?
That's
Like
Thanos,
John
but you're
Stamos.
close. SN 2+, and then the last one is 10, 4. That's Stanek.
Stanek.
Mhm.
Can't stand it.
Yes, and 4+. Safe. I'll give you all a second to scribble them or take a picture or whatever, and I'll post it for you.
Jack.
What? It's not
Just
don't
said-
judge me.
This is just a list of, these are common
I
ones
think
that
you're
you're gonna
your phone
see.
at it for a second. I was like, okay.
I took Tom Brady off my fantasy team and then lost. So I do want to throw this thing. Okay, there you go. That's when he was gonna throw 5 touchdowns. How was I supposed to do?
He's 43. So I swapped him with a younger guy and then.
43?
Yeah.
Well,
That's why he can't
he's
take
still younger
hits
than
because
me.
he's afraid. He
Not
can,
by much. Yes.
he can throw.
Dude's
but
got enough money, why doesn't he settle down already?
Cause homie
Gillette
likes
wants
to.
more. Or not Gillette. What's it?
Gillette.
Gillette.
Well, he was
Shaving.
sponsored by Gillette, but
Yeah.
Giselle. Or is that her
Giselle.
name?
I don't know.
Giselle Bundchen.
Is he married to a model?
Yeah.
I don't know.
Yeah,
I don't keep track of football players.
Gazelle?
it's Giselle, I think. I don't know.
Giselle, yeah.
Bundchen.
So,
Baseball.
Everybody
It's not football.
for tonight,
Yeah.
Everybody gangster.
We're so good with
Gazelle.
all right, y'all. So for tonight,
Gonna be like,
you've got, you're gonna keep your lab in your binder, turn in your homework that you did, and put it up there in the binder. The folder on the top of the chest. And then you guys have a chapter 5 test. Don't panic about that. Use the little sheet. Use the cheat sheet for the naming
Those
flow
are gonna
chart.
be in there?
Huh?
Those are gonna be in there.
No, those won't be in there, but if you need them, you can use those too. I don't mind you guys doing that. It's
You need the flow chart. homie.
yes, the flow chart, and always have your periodic table handy. It's really hard to try and do a test on elements. You can't remember what they are, right? But otherwise, you're good. Do you have any questions? Anyone?
So many. I think.
So many? All right, I think y'all are good.
About life,
Yay.
the class,
We're
the Falcons, Bob quit, why Bill O'Brien got fired. I
Why
there's a
is
lot
this
of
smoking today, huh?